Hi, I'm Tracy Lauderette, call sign Jackie O, Colorado's First Lady fighter pilot. We're at Wings Over the Rockies Air and Space Museum in Denver, Colorado. We're getting an inside look at OSIRIS-REx, unpacking a 2-decade mission to decipher secrets from a 4.5 billion-year-old asteroid.
We're trying to answer the really big question about whether or not we're alone. Is there anybody else out there?
If we really wanted to answer this question, we're going to have to go out and get our own sample of these things.
The team had to solve mind-bending challenges critical to mission success.
Bennu is the trickster asteroid. It challenged us every step of the way. Our plan for getting down to the surface was broken.
So this became an emergency for us.
The most dangerous phase was definitely the sample collection itself. My heart was beating, my stomach was dropping. You only have a single shot at getting some things right.
And I'm like, it's over.
When we finally got the capsule open, 4.5 billion-year-old space material, kind of actually gives me goosebumps.
It's time to go behind the wings.
We live in this beautiful, lush oasis. We have oceans, we have continents, we have life everywhere. When you look around and you see living things all around us, but as we go out in the solar system, all these other worlds, they look dead. Where did our oceans come from? Where did our atmosphere come from? And really, why did life take hold on this planet? My scientific career is really focused on understanding the origin of the solar system, and particularly the origin of the Earth, and why is our planet a habitable environment? And asteroids hold the keys to those questions. Asteroids have played a large role in the evolution of life on Earth. Most famously, 65 million years ago, a giant rock slammed into the Earth, leading to the extinction of the non-avian dinosaurs. We are fortunate that nature delivers to us samples of asteroids from across the solar system, and when they land on the Earth, we call them meteorites.
Meteorites are constantly falling on the Earth from space. Something like 5,000 metric tons per year of material is hitting the Earth. And it's all over the place. And we've been to the far reaches of the Earth to pick these samples up.
We have an extensive meteorite collection on the Earth, but those meteorites, as soon as they land on the ground, they're contaminated with life and water and all of the things that we have on planet Earth.
Antarctica is a natural meteorite concentration terrain. I was there with one of my team members, Dr. Danny Glavin from Goddard Space Flight Center.
And we're looking for organic compounds, the components of life. And so we really need clean samples, pristine materials.
And I'll never forget the moment where we looked down and we saw a meteorite, and it was buried just under the surface of the ice, and it was melting a little pool of water around it, and Danny got really agitated.
The problem is that all meteorites, even in the most pristine place on Earth, like Antarctica, get contaminated by biology.
And we kind of both knew right then, if we really wanted to answer this question, we're going to have to go out and get our own sample of these things and bring them back to Earth. And this has been a 20-year journey.
The OSIRIS-REx mission set out to collect pristine material from Bennu, a near-Earth asteroid requiring a 2.2 billion-mile round-trip journey through deep space. Of all the asteroids out there, what was so scientifically significant that made Bennu your final choice for this mission?
The scientists believe that it has material from the origins of the solar system, but there's more to it than that. Because OSIRIS-REx was a sample return mission, we had to look for an asteroid that was on a trajectory kind of near the Earth so that we could reasonably get there with our spacecraft and get back in maybe a 10-year time frame with the amount of fuel we can carry on board. So Bennu is about the same size as the Empire State Building is tall. If the asteroid's too big, then we don't have enough fuel to navigate down to the surface and back up. If it's too small, there's not enough gravity to even orbit and do some of the complex operations we did. And it allowed us to kind of walk the line between all of these constraints.
The OSIRIS-REx mission to Bennu started in 2001, a partnership between the University of Arizona, NASA Goddard Space Flight Center, and Lockheed Martin.
In the very earliest days of OSIRIS-REx, there was just a small number of us at Lockheed Martin outside of Denver, Colorado, trying to sketch out this incredibly ambitious, multi-decade plan to bring a sample back to the Earth.
Dante Loretta started with the team in 2001 as a deputy principal investigator and became the PI 6 years in. This first-of-its-kind mission required new technology, giving scientists and engineers the biggest challenge of their lives. There were so many potential single points of failure on this mission.
We had our work cut out for us to figure out what it would take to get this mission done. Obviously, the development of the spacecraft is a huge endeavor in itself. You're developing this machine. It has to be completely tested and verified that it will work in the extreme environment of space, because once it's launched, you can't fix it. You have to come up with the design and then start the build process, and you usually have about 4 years to do that. And so that's a big effort just to get to the launch pad.
When we were first designing the OSIRIS-REx mission, we didn't know what the asteroid was going to look like. One thing we did know is that its gravity is really low. It's what we call microgravity environment. It has about the same acceleration on its surface as astronauts experience on the International Space Station. And so when I first started talking to the engineering team, I said, well, yeah, we got to land. We're going to stay on the surface for a while. We're going to use all of our cameras. We're going to pick the rocks that we want to scoop up and bring back to the Earth. And then as they started to look at the microgravity, they're like, that's going to be really hard, because let's say you have a robotic arm and you move it over to pick up a rock, your spacecraft is going to tumble in the opposite direction. So the engineers came back and they said, you know, we're not going to be able to land. So we switched over to a concept that's called the touch and go sampling technique. So that was one of the key decisions that ended up driving the entire spacecraft design.
Fortunately, our partners at Lockheed Martin are really good at building and testing spacecraft and verifying that once you put it together, it's going to survive the harsh environment of space, you know, temperatures and radiation and all of those things. And so there was a lot of testing that was very unique about making sure those pieces would work.
Oh man, this is not like anything I've ever seen before.
We are in the Space Operations Simulation Center, and what we're looking at here is an asteroid wall that we built specifically to test the approach and tag operations for OSIRIS-REx. We use this wall to test the very critical end stage of the sample collection event. We call sample collection tag for touch and go, which is literally because we touched the surface of the asteroid for a brief period of time and then left. One of the important things that this wall allowed us to do was to test the algorithms and the sensors that we needed to achieve the sample collection event. And this includes natural feature tracking, or NFT, which is an image-based process that the spacecraft used to autonomously go from orbit to touching the surface of the asteroid.
OSIRIS-REx had to land on Bennu, collect a sample, and bring it back to Earth. How do you begin translating this ambitious science goal into some of those very specific engineering requirements?
The science requirements are ultimately what drive the entire design of the spacecraft and the operations. How we get to the asteroid, what we do when we're at the asteroid, and then how we achieve the sample collection itself, and ultimately bringing that sample home. It's a lot of hard work by a large number of engineers who are working diligently every day to turn the ideas into an actual spacecraft design. We had to invent an entirely new sampling system that worked in that microgravity environment. This is a unit that we developed to help test the TAGSAM technology before launching the flight unit on the spacecraft. First, we needed to collect a sample in a very short period of time. The second thing is that we wanted to make it as simple as possible, so we didn't want a lot of moving parts. We wanted it to be very reliable. And third, we wanted to make sure it collected as much sample as the requirements specified. And this is what TAGSAM became. And you can think of this as a reverse vacuum cleaner. The pressurized gas would be released underneath TAGSAM, and because the environment of Bennu is a vacuum, the gas is free to expand, and it's basically like a wind. The wind is moving the material from the surface of Bennu inside TAGSAM. It's a very simple device, no moving pieces.
As we got into the details of the design of both the spacecraft and the mission, and one of the things that we did was you had to design them both simultaneously. We really started to learn what it meant to try to operate in microgravity. It's got to do these precision, ultimate, balanced maneuvers to get down to the surface of the asteroid and collect a sample. And then of course you got to make it all the way back to the Earth, and you got to have a capsule that can survive hitting the top of the atmosphere at 28,000 miles an hour. And a parachute has to open up to successfully deliver that capsule back down to the surface of the Earth. And none of that can go wrong.
Let me show you an engineering model of our sample return capsule. This was used to help rehearse the recovery operations for the OSIRIS-REx capsule when it returned to Earth. And this unit is specifically designed to protect the sample from the intense heating that is experienced when you pass through the Earth's atmosphere at very high speeds. As an analogy, a bullet can move at something like 2 kilometers per second. This sample return capsule was hitting the top of Earth's atmosphere at over 12 kilometers per second. Despite the surface temperature of the sample return capsule achieving hundreds or even thousands of degrees, the interior is kept essentially at room temperature.
So you're able to use this to protect this pristine sample through high speed, massive temperature changes.
There are so many moving pieces that have to come together, not just every time, but the first time. You only have a single shot at getting some things right.
In May of 2016, we packaged up the spacecraft, we shipped it to Buckley Air Force Base in Colorado, and I got to ride on a Globemaster Air Force transport vehicle and land at the Kennedy Space Center and start our launch campaign. And for the first time, everybody converged on Cape Canaveral. We knew we were getting ready to launch on this amazing scientific expedition into deep space. It was a beautiful day in Florida, and everything went absolutely flawlessly.
3, 2, 1, and liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
We got off the pad within milliseconds of the opening of the launch window, and we flew on an Atlas V rocket, and it was right down the middle of the path that we had designed, and they put us on the course to asteroid Bennu without any issues.
We need pump speeds and checker pressures are within family. So main chamber pressures have...
Bennu is the smallest object that's ever been orbited by a spacecraft. Once it launches, you have an operations team that's working with the machine, sending commands, doing the plans for what it's going to do. And for this mission, because nobody had explored a small asteroid body like this before, we really had to figure out some of those processes for the first time.
So we're finally here at Mission Ops. Where did you guys control OSIRIS-REx?
If we're doing something on the spacecraft, you would see all of these consoles populated with all of our subsystem engineers looking at their data, sending commands.
Sandy Friend joined the OSIRIS-REx team as a spacecraft engineer and managed mission operations on touchdown. Take me back to the day that you saw images of Bennu for the first time.
So we started to get images of Bennu in the fall of 2018 as we got close, and it was just 1 pixel, then it was 2 pixels. We'd been waiting to see Bennu for years. See it grow from a couple of pixels into an actual image was very exciting, but it was also a little scary because Bennu was much more rocky than we had anticipated.
The team expected to find a relatively smooth surface, but what they found on Bennu was far more dramatic.
The first real images of Bennu showed us that our plan for getting down to the surface was broken. There's nowhere to get a sample. I could just tell right away this was a rough, boulder-covered surface, and I knew right then we were in for a real challenge. The problem was with the guidance system. When you are operating a vehicle in deep space, there's only one thing you can fix, and that's your software. So we needed a software patch. We had to make it smart. We had to give it decision-making capability. We got this, right? We got problems, but you know what? We solve problems. That's what we do on this program.
I can't imagine how you handled that kind of stress.
With all the rocks and boulders on Bennu, we didn't want to take the spacecraft down and touch down on a large boulder and tip over. We had originally planned a laser or LiDAR-based navigation to the surface, but with all of the rocks, that wasn't going to be possible. We did have natural feature tracking on board the spacecraft that was a backup, which is really software that looks for different features as you get close to the surface of Bennu to then tell the spacecraft where it is. So we ended up changing from a LiDAR-based sample collection or tag to an NFT-based one. But that does require a lot of work.
Hopes of any imminent touchdown were put on hold. The spacecraft orbited Bennu while engineers started writing new navigation code. The rewrite took 2 years.
We had to map the asteroid, choose features, load a map, and we even had to go augment that flight software and put in what we call a hazard map.
Hazards were everywhere, forcing them to reevaluate the landing site. So much went into that final decision of the landing site that you guys chose.
So the final site that we picked to do the sample collection, we called it Nightingale. It's really kind of a crazy site. It's about 8 meters in diameter. It has a huge boulder right next to it that's the size of a 2-story building, but it has an area that's relatively free of large rocks, and we were able to verify from this reconnaissance that we did that it had a good chance of having the kind of small particles that would fit inside our sample collection head. Of all of the bad places that Bennu offered up to us, Nightingale was the least bad.
Take me back to that big day where you finally got to collect the sample.
October 20th of 2020 was a very exciting day. We're very nervous.
Position uncertainty is 1 meter.
It's constantly calculating and updating. I think I'm going to be safe, or I think I'm going to hit a hazard. The good news was that number kept dropping. You know, it was a few percent, then 1%, then 0.5%, and then 0.
Hazard probability is 0%.
And that 0% hazard contact, that was the moment I knew, okay, we're in. We're going down to get the sample.
The most dangerous phase was definitely the sample collection itself.
The whole mission comes down to these few seconds.
Literally over a decade's worth of work was being compressed into just a few seconds of contact. The spacecraft was approaching the asteroid at only about 10 centimeters per second.
Attitude control system has transitioned to touch and go mode.
That's about 15 times slower than walking speed. My heart was beating, my stomach was dropping.
Copy thermal go. OREX systems at this time you have a thermal go and systems go to radiate line item 63, product X-ray. India
We got
0.
confirmation that the touchdown had occurred.
We have touchdown!
You know, when we touched the surface of Bennu, it basically exploded underneath us. We excavated a crater that was about 8 meters wide and 0.5 meter deep.
TAGSAM was in contact with Bennu for about 10 seconds in total. We touched down less than 1 meter away than our intended spot. And then we got confirmation that the spacecraft had backed away successfully, and the whole mission control area just erupted in cheers.
Yes! We did it!
It was an incredible moment.
Very exciting, but also there was still an unknown of how much sample did we collect.
There was no expectation of rushing back to Earth. The sole priority was confirming the sample size.
I needed to tell NASA headquarters, I'm confident we got the minimum 60 grams of required material. So we had to back away, and then we had to point the antenna at the Earth, and we started streaming the images back that were taken.
Transmitting the first images of Bennu's sample would take 8 hours.
And there was no way I was going to sleep.
If the sample fell short of the required 60 grams, OSIRIS would have to go back for more. When the images finally appeared, no one was prepared for what they saw.
And the first images come up on the screen, and one of the engineers says, hey, I see a dust particle.
We saw bits of Bennu just floating in space all around it. Every time we moved the spacecraft, we were losing some of it.
And you can just see all this material escaping out of the TAGSAM head. We're bleeding.
So this became an emergency for us. We had collected so much sample that the little flap that's supposed to hold it in was wedged open, and it was allowing material to escape.
We probably filled that sample collector with thousands of grams of sample. But by the time we got it stowed, there was about 120 grams that were left, which was twice what we said we were going to bring back, but about probably less than 10% of what we ultimately collected.
That's about the size of a Snickers bar. It's not very much, but that's the largest extraterrestrial sample that have been brought back to Earth since the Apollo program.
With the sample safe, OSIRIS orbited Bennu for 7 months until the return journey could be synced with the necessary orbital path back to Earth.
In May of 2021, we fired our thrusters and started a 2.5-year journey back to Earth. And we orbited the sun about 2 times to set up a rendezvous with the Earth in September of 2023. Only the capsule re-enters the Earth's atmosphere. So the job was to get the spacecraft targeted to an intersection point with the Earth's atmosphere, release the capsule, and then do a divert burn so the spacecraft would fly harmlessly by the Earth. The first 2 minutes of the capsule entering the atmosphere are the most dynamic parts. It's experiencing 30 times the force of gravity acceleration, and as the atmosphere is causing the capsule to heat to thousands of degrees Fahrenheit as it's entering the atmosphere.
We're at this point in the Utah desert, We take off, the US Air Force is tracking this thing, and you're targeting a patch of Utah desert that's like 50 kilometers across. We get the call out that it's hit the top of the atmosphere and it's entered California airspace. 2 seconds later, it's in Nevada. And then you get into the subsonic regime. You drop below the speed of sound. You don't need your heat shield anymore because you're not heating the plasma up, but you need to deploy a drogue parachute. And 100,000 feet, I'm in the helicopter. I'm like, and the parachute? No sign of the drogue.
It's clear there was no drogue parachute. And then we began to get really worried because that meant that there might be something wrong in the deployment sequence of the parachutes.
60,000 feet, no chute. 50,000 feet, no chute. All the way down to 10,000 feet, and I'm like, it's over. And then the Air Force says, you have main chute. There was a backup. You put redundancy, you put margin on your system, and this is what saved us. There it was, we landed, and it was beautiful. It was perched in the desert. It looked like an Olympic gymnast that had just stuck the landing. It was right on the nose cone, just sitting there. It didn't move, it didn't roll. The parachute was sitting right next to it, and I just broke into tears. And it's just me and the environmental team in the quiet of the Utah desert. And it brought me back to Antarctica, like 20 years in the past, because it had that same sense of being part of something that's bigger than you. All you're doing is hunting for asteroid samples, right? We go through all the recovery operations back to a receiving facility at the hangar. Now it's the excitement of cracking open the treasure chest and seeing what did we actually bring back from this asteroid that I've been dreaming about since we picked it as the mission target in 2005.
And now we get to hand this off to the scientists and the whole new project begins.
And for the first time in our lives, put our eyes on pieces of the asteroid.
So we're headed to NASA's Astrobiology Analytical Laboratory at the Goddard Space Flight Center. And this is where we've been analyzing samples from asteroid Bennu to look for extraterrestrial organic matter.
You mean the actual Bennu samples from the asteroid are in here?
We've got them right here in the laboratory.
For years and years, you guys have been working for this moment.
When we finally got the capsule open and the sample container open, and there we saw this really dark, almost like charcoal colored material, about 120 grams, a little over 4 ounces, a small cupful of this precious material from space. 4.5 billion-year-old space material.
Danny, what can astrobiology teach us about our place in the universe?
So astrobiology is really the study of the origin of life. How did life start on Earth? And the potential for life elsewhere, looking for signs of life beyond Earth. And we're trying to answer the really big question about whether or not we're alone. Is there anybody else out there?
Just little questions.
NASA doesn't do anything small. This is our minus 80°C freezer where we store our meteorites and precious asteroid Bennu samples to keep them frozen and pristine. And so right down here on this shelf, we have our samples here. You see the powder in the vial.
Wow.
So right now I'm grinding some actual Bennu sample. We take some of that powder, put it into a test tube with water, seal it, and then we boil it, 100°C. We basically make a Bennu tea. So we're extracting all the good stuff, all the organic compounds from the solid powder into the water. We're able to separate out all of the organic compounds and detect them by mass to identify them, by studying these space rocks to look for the chemical building blocks of life.
We just made Bennu tea out of asteroid powder that came all the way from deep space. Who knows what mysteries of life will be unlocked in these samples?
One of the things that got me the most excited was the detection of amino acids. These are the compounds that are needed to build proteins in all life on Earth. And in fact, we found 14 of the 20 essential protein amino acids in life on Earth. Just incredible. These are the basic building blocks of life.
So was Carl Sagan right? Are we actually made of stardust?
Sagan was absolutely right. I mean, we're all made of the basic elemental building blocks of life. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, all of these things, were made in stars and eventually incorporated into asteroids like Bennu. The genetic components of DNA were found in Bennu. Kind of actually gives me goosebumps to think that the discovery of the building blocks really, I think, increases the odds that life could have started somewhere else. This is only the beginning. It really is. We've made some big discoveries already, and I expect there'll be many, many more over the next 10, 20, 30 years. We're still looking at samples collected from the moon over 50 years later, learning new things about the lunar samples. And the same will be true for Bennu.
120 grams, that's a lifetime of material for any sample scientist. It is a universe of material for us to explore, and generations will be looking at this for decades, if not centuries into the future. Not only did the Earth get all these compounds, but they went to Venus, they went to Mars, they went to the moons of Jupiter, Saturn, the outer solar system. All these places got the same kit that could make life. Still, the mystery is, how did they go through that transformation to become alive? We don't know.
We are only just beginning to scrape the surface of scientific research from the Bennu asteroid samples. The OSIRIS spacecraft mission is not over. Now it's headed to asteroid Apophis for its next chapter of exploration. We'll see you next time on Behind the Wings.